Welcome to this third lecture now. It is the second lecture in the part on real life reactors. Uh, Before you go forward, make sure that you have done homework for the previous lecture, whatever was assigned. Let's start this lecture by looking at some of the things that we are going to do. First of all, this is where we are in the course. We are on real life reactors, design aspects. These are the things that we are going to do. Previous lecture we have seen, first of all, we have tried to look at one case study where we had to design a reactor for making a certain tons per or so many tons per hour or tons per year of a product. Just a couple of questions just to refresh your memory. First of all, what type of reactor is preferred for slow reactions when rate constant is far less than 0.1 minute inverse? Qualitatively explain the reasons for your answer. What type of reactor is preferred when you have fast reactions, rate constant far greater than 0.1 minute inverse? Qualitatively explain your answers. Again, a small revision problem. Let's say a reaction A going to products shows the following kinetics. Ra is kCa divided by 1 plus kCa square. We will see where these kinds of kinetics come as we go along in the course. Let's say rate constant K is 0.1 minute inverse and capital K is like a equilibrium constant is 20 into 20 meter raised to 6 kilomole square, because it's a second order. It is kCa square. In a plant, it is desired to carry out the reaction in a continuous manner with inlet concentration of A as 0.001 gram mole per centimeter cube and molar flow rate of A in the reactor at 5 kilomoles per hour. In the plant, two reactors are available: one 6 meter cube continuous well mixed, or two 6 meter cube continuous plug flow reactor. Now you see, I am not saying CSTR, I am saying continuous well mixed. Okay, and I should be also saying steady state. Recall the classification that we have done. Based on that, we should be speaking now, not very loose, not loose terms like we used to do in our undergraduate course. Or 6 meter cube reactor continuous flow manner. Assume that your boss has asked you to choose either of these two reactors for carrying out reactions, and what would be your reply? So solve this problem, and it will be a sort of revision of what we have done. Okay, so this is where we had stopped our previous lecture. We had looked at a reactor selection decision tree. When reaction was slow, we said that batch reactor is preferable, although recall, go back to previous lecture if you want, although plug flow reactor is cheaper, but it is not convenient because you have kilometers of length, several kilometers you had got, right? Whereas batch reactor, which is maybe 30 meter cube, is what we had done for our last example, and maybe several 4-5 batch reactors, 30 meter cube reactors we could use, or we could have used well mixed reactors in series instead of a plug flow reactor. This will come when we start doing out things on RTD. When we had fast reactions, rate constant far greater than 0.1 minute inverse, reaction time was in seconds. And if reaction time was in seconds, that means our reaction is very fast and we can use very well our plug flow reactor. Okay? Or we could also use a single well mixed reactor. Now this choice depends, although plug flow reactor is cheaper, sometimes you would want a well mixed reactor for some other considerations which we will see in our subsequent lectures, including this lecture. So what we want to address in this lecture is, in this selection, in this decision making tree, how does heat transfer considerations affect the reactor selection? Remember, our previous lecture and all our undergraduate course we had done, we had assumed that reactor was operated isothermally, so rate constant does not change with either time or with respect to location, time in a batch reactor or with respect to location in a plug flow reactor. So this is what we want to do in this lecture. How does heat transfer considerations come into picture in this kind of scenario? So here is a small problem. Let's say there is a liquid phase reaction A going to P is going to be carried out in a continuous adiabatic reactor operating at steady state. Now I'm using the classification that we had talked about: continuous, adiabatic, steady state. Okay. Feed to the reactor has a flow rate of 15 meter cube per hour. Concentration of A is 10 kilomoles per meter cube. Temperature is 330 Kelvin. Rate constant is 330 hour inverse at a temperature of 360 Kelvin. Reaction is exothermic. Delta H is minus 1.65 kilocalories per gram mole. Activation energy is 15.7 kilocalories per gram mole. Specific heat of reaction mixture is 0.6. Density of the reaction mixture is 600. Assume that the properties do not change with temperature. It is desired to have 70% conversion of A in the reactor. Calculate the reactor volume required if we have a well mixed reactor. So we have a well mixed continuous adiabatic reactor or a plug flow reactor, continuous adiabatic steady state. Okay. This is actually a solved example 8.3 on page 490 in the 4th edition of formula. So you might want to read that as well. Okay. So pause the video, solve this problem for yourself. Remember, now it's an exothermic reaction. Okay, pause the video. If you have issues, see the book as well, but solve it yourself, then only go forward. Okay, let's think about a well mixed reactor first, right? A well mixed reactor, what is it going to look like? Well mixed reactor is going to look like our well mixed reactor. Let's just put that pointer. Yeah, well mixed reactor is going to look like this. There is a tank, agitator to make it well mixed, flow rate, incoming flow rate, inlet concentration, inlet temperature. It comes in, now it is well mixed. So what does that mean? Concentration and temperature anywhere in the reactor is constant. It is same equal to outlet concentration. So outlet flow rate is F, Ca0 is the outlet concentration, outgoing concentration, T0 is the outgoing concentration. Now this reactor, everywhere inside temperature is T0, everywhere inside concentration is Ca0, right? What we want to find out is this volume. Okay, so a little bit about our kinetics. First of all, what is our kinetics? Our kinetics is 30 hour raised to minus 1. Let's write that. 30 hour raised to minus 1 at 360 Kelvin. Energy of activation is 15.7 kilocalories per gram mole. Right? Now, if you write K as K0 exponent of minus E by RT, what do we know here? K is 30 hour raised to minus 1. K0 is what we want to find out, exponent of minus E by R. Now take care of units. E is 15.7 kilocalories per gram mole. So minus 15,700 calories per gram mole. R you can take 1.987 calories per gram mole Kelvin, and temperature is 360 Kelvin. Right, take care of units. This is kilocalories per gram mole. R is 1.987 calories per gram mole. So take care of units. So this, if you find out, you will find K0 as 1.02 into 10 raised to 11 hour raised to minus 1. Now what are we going to do? We are going to take control volume like this, and on this control volume we are going to say whatever comes in minus whatever goes out must be equal to what is reacted. So flow rate multiplied by inlet concentration Cai minus Ca0 is equal to K Ca0 outgoing concentration, Ca out, right? V is the reactor volume here. This K we can write in terms of K0 e raised to minus E by RT0. Why is that? This K is at this, the K that is written in this material balance is at a temperature of T0. It is at a temperature of T0. whereas K is 30, our inverse at 360 Kelvin. 360 Kelvin. Okay. Because reaction is exothermic, heat is generated, and if this is an adiabatic reactor, remember it is a continuous adiabatic reactor, temperature will rise. So temperature inside the reactor T0 is going to be more than the temperature at which it is fed. It is fed at a temperature of 330 Kelvin. Right? So temperature is going to be greater than Ti. T out is going to be greater than Ti. So Ti is 330 Kelvin. That means T naught is going to be more than 330 Kelvin. It may be 360, it may be 365, it may be 362, it may be 340, it may be 390. That depends on this heat of reaction, delta H. Okay, now same way, can we write heat balance? Enthalpy balance, if we write on this control volume, F flow rate into rho into Cp into Ti is the enthalpy coming in. Look at the units. Flow rate, if you like, is in meter cube per hour. Rho kg per meter cube. Right? We are writing units of this. Cp is whatever units I have given to you. Kilocalories per kg Kelvin. Kilocalories per kg Kelvin. Multiplied by temperature Kelvin. So this will cancel out. This will cancel out. This will cancel out. We will get rate at which enthalpy enters, kilocalories per hour. Okay, enthalpy in plus whatever enthalpy generated. What is the enthalpy generated? It is the rate, how many moles react per unit time, rate of reaction multiplied by heat of reaction. So K Ca naught into V. Recall, now this is K Ca naught into V. What are the units of K Ca naught into V? 1 K has units of 1 per hour. Ca naught kilomoles per meter cube. Okay. V meter cube. Delta H kilocalories per gram mole. Now be careful. Concentration is in terms of kilomoles per meter cube. Heat of reaction is in kilocalories per gram mole. So I'll have to multiply that by 1000. Then only I'll get it kilocalories per kilomole. Right. So this will cancel out. This will cancel out. We will have kilocalories per hour. That is the rate of heat generation. Be careful about units. Adiabatic, so whatever is in plus whatever is generated must be equal to what is going out. Right. So now I can rub this out. It was just to show you the units. You have to be careful about units. We are writing the rate at which enthalpy comes in, the rate at which enthalpy is generated, and rate at which enthalpy is going out. Right? I can rearrange this little bit and get F rho Cp T out minus T in must be equal to K naught exponent of minus E by RT 0. Again, this K can be replaced in terms of K naught exponent of minus E by RT naught. Ca out V minus delta H. Right? Remember, important point, T0, T out is TO, T out if you like. The reactor is operating at T out. Right? It is different from 360 at which the rate constant is given to you. It can be same, it can be different as well. Now if you take these two equations, can you see the common part? Now let me rub this part also. Right, now we have seen how all these things, how the units of all these things are written. Let's rub. Right, you see the common part here. K0 exponent of minus E by RT 0, Ca naught, that's common, and V as well. Whole right hand side is common. So I can write F C naught, F rho Cp T naught minus Ti. This whole thing I can write in terms of F Cai minus Ca0 into minus delta H, and then F also I can cancel out from here, and then we'll get rho Cp T naught minus Ti is equal to Cai minus Ca out into minus delta H. Now what do we want? We want 70% conversion of A, right? Ca in, Cai is 10, so that means Ca out is 3 kilomoles per meter cube. Right? Let's put all these things. Now, what do we know now? Use this expression. What do we know here? We know rho, we know Cp, T naught we don't know, Ti we know, Cai we know, Ca out we know, delta H we know. So we can calculate T out from here. T out will become 362.1. You just simplify 600 rho Cp 0.6, T naught what we want to find out 330 is the inlet temperature, 10 minus 3 Cai minus C out 1.65 into 1000. So this is 1.65. Delta H is kilocalories per gram mole and Ca is in kilomoles. Take care of units. So we want it in terms of kilocalories per kilomole delta H. Right? So it is 1.65 into 10, 1000. Recall from here, just let me take you back a little bit. What do we know here? What do we know here? In these two equations, 1 and 2, what do we know? F we know, Ca in we know, Ca out we know, we want 70% conversion, K naught we know, E we know, R we know, T naught we don't know because it's exothermic reaction. It is outlet temperature. Ca naught, that's what we know, right? And V, do we know V? No, we don't know V. We want to find out V, right? So T naught we don't know and V we don't know. That is one equation. Here also in the enthalpy balance, what do we know? F we know, rho we know, Cp we know, T naught we don't know, Ti we know, K naught we know, E we know, R we know, T naught we don't know. Okay, Ca naught we know, V we don't know, delta H we don't know. So T naught and V are the two unknowns in these two equations. T naught and V, properly, T naught and V, these are unknowns, right? So we have to solve them together. One way of solving them is to eliminate one of the variables. V we have eliminated by using equation 1 and 2, right? By writing the right hand side, we have eliminated V, and then therefore we got expression for T naught, and therefore we got a value of T naught. Now this T naught we can substitute in any one of the equations, right? First one or the second one, it doesn't matter. So if you substitute in equation 1, because T naught appears only on one side, we can calculate the volume, and you will find that volume required is 1.03 meter cube. Okay, so check that. Solve this again for yourself. If you have not understood, take a pause, solve, understand all the terms that we are writing, then only go forward. Okay, same way, if I have to write solution for plug flow, what do we know now? For a plug flow, what are we going to do? We are going to take a differential element like this, and we are going to write material balance. So our first is material balance, and this equation is enthalpy balance. Materials balance, what we are going to write? Flow rate into concentration at V minus flow rate into concentration at V plus delta V. This is in minus out. In minus out must be equal to what is reacted. Reacted is K naught exponent of minus E by R. This is T naught. Okay. Ca. Well, sorry. This is T. T is at any V. T is going to change. Inlet temperature is our. Look at the inlet temperature. What is the value? Inlet temperature is 330 Kelvin. Look at this. Right? So inlet temperature is 330. It's an adiabatic reactor and exothermic reaction. So temperature is going to rise with respect to distance along the reactor. So this T is going to change with this reactor location. Ca is going to change from inlet to outlet. Delta V is the volume in that control, in that small differential element. I can rearrange, divide by delta V, take limit as delta V tending to 0, we'll get dCA by dV is K naught exponent of minus E by RT, Ca and F. Or you can keep the F here and write it in terms of tau, residence time. So dCA by d tau is equal to K naught exponent of minus E by RT into Ca. So this is one equation. Make sure that you get this yourself. You are able to write it yourself. Okay. Same way, enthalpy balance. What we can write? Whatever comes in plus whatever is generated must be equal to what is going out. Enthalpy coming in is rho Cp T at F rho Cp T at V. Generated K naught exponent of minus E by RT, that is K, into Ca into delta H into delta V. Right? Look at this. And F rho Cpt going out at V plus delta V. Okay. Rearrange, divide by delta V, take limit as delta V tending to 0, and you will get this expression. dt by d tau is K naught exponent of minus E by RT Ca minus delta H by rho Cp. Now again, like last time, let's try to identify. This Ca is going to change with respect to entry to outlet. K naught we know, E we know, R we know, T is going to change with respect to location. Ca is going to change with respect to location. Ca is going to change with respect to location. Location in the sense, now with respect to residence time we are writing. This T is going to change with respect to tau. K naught we know, E we know, R we know, T is going to change, Ca is going to change, delta H we know, rho we know, Cp we know. But like last time, we can write these two together and write dt by d tau left hand side of this. We can write it as the, look at the common term. Again, look at the common term. Just let me rub this. Look at the right hand side. Right hand side is K naught exponent of minus E by RT into Ca. The same thing appears here. K naught exponent of minus E by RT into Ca. That is the rate expression. Right? So I can simplify as T minus Ti is equal to Cai minus Ca is equal to delta H by rho Cp. Which means temperature at any location would be inlet temperature plus Ca inlet minus Ca into minus delta H by rho Cp. Now what do we know here? We know Ti, we know Cai, we know delta H, we know rho and Cp. So this gives us a relationship between temperature and Ca at any location. If I know Ca at that location, I can calculate temperature, right? So what are the unknowns? These are the two equations, one equation here, second equation here. We don't know T and Ca. So if I relate T and Ca using this equation, I need to solve only one equation, and one equation we will solve for dCa by d tau. Right? So K naught exponent of minus E by R. T now I can replace as from here. Correct? Into Ca. That is our equation 1. Rewritten equation 1. Rewritten using this expression. Okay. Now you can substitute the values. All we have to do is integrate now from inlet concentration 10 to the outlet concentration. We want 70% conversion. So outlet concentration will be 3, and from 0 to tau. So if you can do this now. Well, one more point. This is a numerical integration. Either you can do this in Excel or any spreadsheet software, use trapezoidal rule or Simpson's 1/3. Nowadays, calculators are powerful. If you have FX 991 ES Plus, you can do this in a calculator as well. So learn how to do integration on calculator. It's going to come in very handy because we have to do these kinds of integrations very often. And what you will find is that volume would be 1.46 meter cube. Does that ring a bell? Does that sound an alarm bell or any bell in your head? Look at the previous slide. 1.03 meter cube for a well mixed reactor. Now 1.46 meter cube for plug flow reactor. What do we have? Volume of CSTR or residence time for CSTR is less than volume of PFR. How is that possible? Why did this happen? Try to answer this question. Try to answer this question for yourself. This is not what we had learnt in our undergraduate course, because in our undergraduate course we had only looked at isothermal processes. Now we are going to look at exothermic reactions, endothermic reactions, adiabatic processes. Why did this happen? Think. Pause the video, think for yourself, find out answer for yourself. That's the joy of learning. That's the beauty of learning something new. To figure out how things happen, why things are different, why things are not as per our expectation, as per our whatever we have studied in our undergraduate course. Something different has happened. What is the difference that has happened? It is an exothermic reaction. And because it's an exothermic reaction, what has happened? You see, in a CSTR, in a well mixed reactor, temperature everywhere is T0. Temperature everywhere is higher. T0 is 362. Temperature everywhere was 362. Whereas in a plug flow reactor, inlet temperature was 330, outlet temperature is 362. Why it is 362? Because from our this expression, if we substitute now outlet condition, what is the outlet condition? If you use this expression, Ti would be equal to Ti is 330 plus CAI is 10 minus CA outlet if I want. Outlet is 3, CA outlet is 3. Delta H is 1.5 kilocalories per gram mole, 1.5 into 1000 divided by rho. Rho was 600 and 0.6 was Cp. 600 and 0.6 was Cp. Look at this. This will be 1500. 1500 divided by 600 will be 2.5 divided by 0.6. Right? Some 40s into 7. 28, 29. Right? 4. So this will be T out will be 362.1, whatever that value is. Right? So inlet is 330, outlet is 362. So rate is increasing with respect to location, but most of the time rate is below 362. Rate is below at a temperature is below 362. So rate is not as high. Whereas in a well mixed reactor, reaction rate everywhere is high. That's why it required lesser reactor volume as compared to plug flow. See this? Such things can happen if we are talking about exothermic reactions. Pause the video, make sure that you have understood everything that we have discussed so far. Make sure that you can derive all these expressions for yourself. Right? Whatever expressions you have seen in these slides, make sure that you can derive them yourself. Make sure you have taken care of units. Okay? Some of these things we have to be very, very careful. Understand, then only go forward. Then only go forward. If you have not understood, pause, ask some people, ask your friends. Okay, just a couple of problems I want to give you just for practice. So imagine that in a plant, continuous nitration of an organic compound A is being carried out with a nitrating mixture. Well, let's simplicity assume that it's a homogeneous reaction, first order, A going to products. Let's say this reaction is being carried out in 1 inch, 25 millimeter inner diameter, 100 meter long coil tube. Since the reactants are corrosive, tube has a glass lining on the inside, As a result, it may be assumed that the reactor behaves like an adiabatic reactor. Liquid flow rate to the reactor is 5 meter cube per hour. Concentration of A is 0.5 kilomoles per meter cube. At a temperature of 50 degrees centigrade, the reaction is exothermic. Delta H is minus 70. Energy of activation is 30. It is observed that the outlet temperature is 90 degrees centigrade. Some physicochemical properties of the liquid mixture are, assume these properties do not change with temperature, appearance, pale yellow liquid, molecular weight, density, all these things are given, viscosity, specific heat, thermal conductivity is given. What is the percentage conversion of A in the reactor? Okay. What is the percentage conversion of A in the reactor? And on some day, if the inlet temperature decreases to 45 degrees centigrade while maintaining all other conditions the same, what would be the steady state percentage conversion of A in the reactor? Solve this problem for yourself. I don't have a solution. Pause the video, solve it for yourself. Just to help you solve, let's try to draw first of all. First condition is there is a plug flow reactor, 25 millimeter inner diameter, 100 meter long. Let's imagine that this is a straight tube, but right now it's a coiled reactor. So inlet flow rate is flow Cp or C rho F Ca Ti, T inlet, outgoing F Ca out, T out. Okay. Delta H we know, everything we know. Delta H we know, energy of activation we know. Right? If you write the same expressions as last time, right, try to think what is known, what is not known, okay, and try to calculate whatever is unknown using these two expressions. Let me rub out all this now. Use these two expressions. For this particular problem, what do we know? We know inlet outlet temperature, we know inlet outlet concentrations, we know inlet outlet temperatures. What else do we know? Delta H we know, energy of activation we know. Right? What else do we know? Try to find out whatever is unknown in these two equations. What things are known, what things are unknown. Okay? Try to find those out. Okay. Now, second case, what are we asking? On some day, if inlet temperature, instead of inlet temperature usually is 50 degrees centigrade, this suddenly becomes from 50, it becomes 45. What would be the conversion in the reactor for this particular inlet temperature? So then if conversion is dropping very significantly or changing very significantly, then we know that we have to maintain this temperature properly. Process control becomes important. That's the learning that we get. We need to control inlet temperature properly. Right? So write what we know in these expressions, these two expressions, and try to find out whatever is unknown. Do this for yourself. Okay. Here's another problem. Liquid phase reaction A going to product was being carried out in a continuous well mixed reactor. Having a liquid volume of 0.2 meter cube. Rate constant was at 40 and 50 degrees R, 1.127 and 1.421. Feed to the reactor is pure A with concentration of 10 kilomoles per meter cube, 40 degrees centigrade at a rate of 0.2 meter cube per minute. Heat of reaction is given to you. Density, viscosity are given to you, specific heat, thermal conductivity are given to you. Assume that the physical properties are independent of temperature and composition. The reactor is equipped with a jacket for cooling, heating purposes, having an area of 5 meters square. Steam is supplied to the jacket which condenses at a constant temperature of 150 degrees centigrade. Overall heat transfer coefficient can be taken as 500 kilocalories per hour per meter square. Calculate the conversion in the reactor. Okay, I don't have a solution. So do this problem for yourself. Pause the video. Do this problem yourself. Let's try to see some solution. Let's try to quickly see some solution. What do we know? We know that there is a well mixed continuous reactor. Let's draw. Good idea to draw a picture, a schematic representation. There is a jacket. Oops. There is a jacket. Okay. There is an agitator, liquid. Liquid enters, goes out. In jacket, what are we told? We are supplied steam and it condenses, liquid condensate. This jacket temperature is 150 degrees centigrade. Steam is at 150 degrees centigrade. Feed, so flow rate, rho, so flow rate, inlet concentration, inlet temperature, flow rate, outlet concentration, outlet temperature. Well mixed, so concentration everywhere is equal to the outlet concentration Ca out, temperature everywhere is T out, volume is V. Right? Go back to our CSTR solution, well mixed reactor solution. We have these two expressions. Let's rub out all these things. In these two expressions, try to write what is known to you and what is unknown in these expressions, and then try to solve for what is not known. Okay? What is not known? There is only one additional term, that this will only change was this is an adiabatic reactor, whereas this now is a reactor where there is heat is being transferred in the jacket. So if I write, so material balance, if I write flow rate Ca in minus Ca out, in minus out must be equal to what is reacted, K naught exponent of minus E by R T naught into Ca naught into V. Okay, first order reaction. Oops. Look at this, there is a typing error. Let me correct that. Let me correct that. Rate constant is meter cube per kilomole per minute. So it's a second order reaction, you see. So this was our reactor jacket. F Cai Ti, Ca out T out V, what goes out, F Ca out T out. So material balance, if we write, what comes in minus out, Cai minus Ca out is equal to what is reacted, K naught exponent of minus E by R T naught Ca out into V. Okay. Heat balance, if we write now, wait, this is now, this is a second order reaction, right? So it is Kca square. Take care of units. Heat balance. What comes in? F rho Cp T in. What is generated? K naught exponent of minus E by R T naught. This is K Ca square minus delta H into V. Whatever comes in plus what is generated plus what is added. There is steam condensing here. Condensed. What is added? What is added is heat transfer from jacket to the vessel. U A temperature of steam minus temperature inside the reactor. U 500 area we are told somewhere 5 meter square. Temperature of steam we are told 150 degrees centigrade. What comes in plus what is generated plus what is added must be equal to what is going out. F rho Cp T out. These two equations if you solve, again you can see that this term is common. This term is common. Right? Only delta H is different. Right? So again in these two equations write things that you know, write things that you do not know, and then solve these two equations and you will get what you do not know. Okay? So do this problem for yourself. Again I am repeating, do not go forward unless you are able to write all these heat balance, mass balance on a small control volume. Only when you are able to do that, then only you go forward. Because now more and more complicated things are going to come. So you should be able to do all these balances very easily now, very quickly now. These are material balance, energy balance, something that we have done in our undergraduate course, right? MEBC is one of the first courses that we do in our chemical engineering curriculum, and that is what is required now for our reactor design, CRE. It's nothing but material balance along with your reactions. Go forward only once you are comfortable doing all these things now. Okay, let's go forward. Okay, so imagine that we have a batch reactor. Can you write an expression for heat generation rate? Can you tell me when is the heat generation rate maximum? Pause, do it for yourself. So, rate is Kca. Let's say it's a first order reaction. Heat generation rate would be Ra into V into delta H. So, Kca V into delta H. This is what we have been writing. Rate of heat generation. When it will be maximum is when K is a constant if provided it is an isothermal reaction. Else K will change with respect to time. Ca will change with respect to time. Volume is constant, delta H is constant. It's a property provided. Delta H can change with temperature, but if we are saying that delta H is not a very strong function of temperature, then delta H is constant. So usually if let's say it's an isothermal reaction, then CAI would be, rate of heat generation will be maximum at the initial condition, CAI, at T equal to 0. That's the maximum concentration. Okay. Now let's say heat is being taken out by this jacket that is here, right? So jacket is here and there is, let's say, a cooling water out or return and cooling water supply. Let's say Tc is the coolant temperature. When will the reactor operate isothermally? Is when we match the rate of heat generation to rate of heat removal by cooling. So let's write that UA delta T log mean, that's our heat removal rate, and this is our maximum heat generation rate, rate of heat generation. We can rearrange this expression to tell us what is the difference in the inside temperature minus the outside temperature that is required. Delta T log mean would be KCAI T minus delta H divided by 4U. Now just to tell you, this V by A is a volume of liquid divided by area of this jacket. What is volume? Volume is pi by 4 T square into H, if you like. This is our height H. T is the diameter. We are neglecting volume of this dished end. And area is area of heat transfer, pi into T into H. Okay. So then this V by A would become T by 4. Now what I want you to do is plot this delta T Lm required for different values of K, for different values of Ca, for different values of delta H, for different values of T, and different values of U. I'm just going to show you two considerations. Okay, how it changes with delta H and how it changes with the tank size T, reactor diameter. Let's take some values. Let's say T is 3, CAI is 1, U is 300. Plot LMTD required as a function of delta H from this expression. That's one. Second thing, how tank size affects. Take these values, plot how LMTD required changes as a function of tank diameter. Here is what you will find. The peak LMTD required changes if delta H is changing. This is how it changes. So for small delta H, say maybe 10, 20 kilocalories per gram mole, we require only 20-30 LMTD, which means if I have cooling water which is available at 30 degrees centigrade, I can easily operate a reactor which is at 60 degrees centigrade. Delta T is available is 30, right? Whereas if I have heat generation rate which is higher and higher, I require more and more delta T. So if I have a heat of reaction as 100 kilocalories per gram mole and I want to operate the reactor at, let's say, 120 degrees centigrade, I need 140 degree or 150 degree delta T, which means my cooling temperature has to be minus 30, not cooling water, not plus 30. So this tells us what is a feasible window of operating exothermic reactions in a batch process. If we try to operate these kinds of reactions with this high delta H, obviously heat removal rate is going to be smaller than heat generation rate. Reactor temperature is going to rise, and therefore it may lead to runaway conditions, become unmanageable. This is 10, 20, 30, 40, 50. So that means here our delta T required is 70. So that means if cooling water is there, I can have my reaction temperature of 100. But if I don't have that delta T, then temperature will rise because heat removal rate will become less than heat generation rate. We are going to do all these things even more now. Okay. Second thing, based on tank diameter, smaller the tank diameter, what does that mean? Smaller tank diameter means I have good heat transfer per unit volume. Good heat transfer per unit volume. Then I require a small delta T to maintain isothermal conditions. Whereas if I go to plant scale, 2 meters, 3 meters, 4 meters, 5 meters diameter, I require delta T of 250 degrees centigrade, which means if I am doing reaction at, let's say, 150 degrees centigrade, I need cooling medium which is at minus 100 degrees centigrade. Then only I will be able to maintain isothermal conditions. Otherwise, it will lead to runaway conditions. Heat removal rate is less than heat generation rate. So this can lead to runaway conditions. So batch exothermic reactions, we have to be very careful. They can lead to runaway conditions. Runaway means temperature rises abnormally fast. Why? Because the heat removal rate becomes less than what my heat generation rate is. So temperature keeps on building. Okay, let's write it for a well mixed reactor now. Okay, so if we have a well mixed reactor, can we write a heat balance? We have already done that using a jacket. Now we are rearrange this expression. Okay, here is our expression. So this is the heat removal rate in the jacket. What comes in? Enthalpy in, enthalpy out, enthalpy generated, right? So delta T log mean required between the reactor temperature and the cooling temperature, cooling water, let's say it is at a cooling temperature is, let's say, Tc, heat generation plus whatever heat is added by inlet flow rate divided by UA. Now again, do this, we want to do this for different situations. Heat generation rate is constant, that's an advantage. Heat generation rate is lower due to back mixing because concentration, it doesn't react so much. It can be removed by feeding cold reactant. That's an option to us. If Ti is lower, then this is negative. It will take away some enthalpy of reaction. That's one way of controlling temperature in exothermic reactions in a well mixed reactor. So plot how delta T Lm requires with changes with the parameters, especially how delta T Lm required changes with, let's say, heat of reaction. Same way now do it for plug flow reactor. So if you look at this, if you look at this kind of concentration, we require only 14 degrees of LMTD, easily manageable, right? But we can now see what kind of considerations are required. Okay. Same way for a plug flow reactor now. Right, material balance, heat balance on a differential element, derive expressions for dCA by dV and dT by dV. We have already done this. Let's do this very fast. So you will get this dt, right? So this is heat generation, in minus out, or material balance, and heat removed. There is a jacket now. What we are saying, there is a jacket. The jacket is at a temperature Tc. Inside temperature is T at any location, of course. T is changing. Tc we are assuming it to be constant. Tc is the same at all locations. Cooling water like 30 degrees centigrade throughout if I maintain high enough flow. Okay, so what we need to do is we need to solve these two equations together, like what we had done in our earlier case. Then we can think about, so this surface area to volume ratio is very, very critical now. You see, 4 by diameter of the reactor. D is the diameter of the reactor. D. Right. So if diameter is 1 meter, surface area per unit volume is 4 meter square per meter. 0.1 meter, 10 centimeters, 40. 1 centimeter, 400. 1 millimeter, 4000. 100 microns, 40,000. Now you see how extremely exothermic reactions can be managed by increasing surface area to volume ratio by going to smaller and smaller reactor diameters. There is a very fashionable word these days for these kinds of reactions carried out when in small sized tubes, microreactors, right? Okay, here is qualitatively, if I want to sketch temperature versus length, if it's an isothermal, temperature would be constant. Adiabatic, temperature will rise with respect to location. Diabatic means temperature will change, but I have heat removal also happening and heat generation is also happening. Heat removal is not enough to maintain isothermal, so it goes up, but then once the temperature rises, then the heat removal rate becomes faster and faster. The temperature difference becomes larger and larger, and then we get what is called as a diabatic condition. So now plug flow. So based on this, based on these two, we can derive an expression for what is the maximum outlet temperature for an adiabatic operation, right? So this is what we had seen earlier. This we had seen earlier in our problem. Adiabatic means this U is 0. Adiabatic. And then this we have seen this. These two expressions. Right? Recall these two expressions. They are the same. They are same here, you see. Same here. These two expressions. So maximum adiabatic temperature rise we can find out from these two, combining these two. If you combine these two, what was our expression? T is equal to Ti plus Cai minus Ca minus delta H divided by rho Cp. This is what we had earlier. What is the maximum possible value is when Ca is 0. So delta H into Cai divided by rho Cp. That will give us the maximum temperature rise. That's the temperature rise across the entry to exit. Okay. So assume some values of delta T max, assume some values and plot how delta T max varies with Cai and delta H. Here is what you would have plotted, what you will get. So here is inlet concentration. You see, this is a 3D graph. Inlet concentration, heat of reaction, and these colors indicate what is the temperature rise. This is 0 to 10, this is 10 to 20, 20 to 30, 40 to 50, and so on and so forth. So if our inlet concentration is 1, if our heat of reaction is minus 50, we get a maximum adiabatic temperature rise of something like 90 to 100. Whereas if your reaction is small, if our inlet concentration is small, if our heat of reaction is small, we get a very small heat of reaction. So we use these expressions, we use these kind of charts to quickly assess what is going to be the maximum temperature rise. Now at this maximum temperature rise, what problems could be there? Our reactants could degrade. They could lead to runaway conditions, or solvent could vaporize, suddenly flashing will happen, suddenly vapor generation will happen, pressure will increase, reactor will burst, all these kinds of things will happen. We use these expressions to identify whether such things can happen, and only way we can control that is if I allow heat to be transferred out and take small enough reactors to maintain high surface area per unit volume, generate high surface area per unit volume, then I can have enough heat transfer and I can maintain isothermal conditions. So micro reactors or flow chemistry, two words are very common these days, right? They are nothing but plug flow reactions in using and including heat transfer considerations. Another thing that we need to think about for a plug flow is what is the temperature rise across the reactor. So if I say Tc is the coolant temperature here, right? What is the temperature at the center line of the tube as compared to the wall of the tube? Right? So we want to find out rate of this temperature difference between, let's say, center line and wall, because that is what is like a hotspot that is generated. You may have a catalyst here, you may have a reactant that is there that may degrade at these hot conditions. What I want you to do is write rate of heat conduction from center to wall. Heat conduction, Fourier law, minus K dt by dx into area, right? Or flux, if you write, is just minus K dt by dx. Rate of heat generation, we have written it enough number of times. Heat generation, we have written enough number of times. Heat generation. Right. So K, thermal conductivity. Now it's not rate constant. That's why I'm writing KT, thermal conductivity. Area, dt by dr in the radial direction. Right. And KCA minus delta H, volume, pi by 4 d square dl. So if you equate them, you will get what is the maximum temperature at rise across the center. Right. So just rearrange these expressions. R I am writing as d by 2, dl is cancelled out from both sides. Okay. Delta T, that's the temperature rise between the center and the wall. Delta H K Ca d square 8 kT. Now same way, if I do now, we can define a dimensionless parameter beta as delta T divided by delta T max. What is the maximum allowable temperature gradient? Right? Let's say for a particular reaction, maximum allowed is, let's say, 30 degrees centigrade. Then we can find out this delta T, we can write in terms of beta. Right? Beta would be delta H K Ca d square 8 delta T max by kT. This is dictated by different conditions, by safety, by let's say by the properties of the mixture. Safety. I don't want delta T more. Maximum delta T I want is say 5 degrees, or maximum delta T I can tolerate is, let's say, 30 degrees or 50 degrees. This is what we have to know based on material that we are handling. Some material degrades, corrodes, maybe char, something that happens, right? Or catches fire, right? Auto ignition temperature. This beta now we can calculate, and if this beta is less than 1, we are safe. Right? Beta is more than 1, oh, we are in danger. Okay? So this beta now, delta H is a property, K rate constant, inlet concentration, delta T max safety, thermal conductivity is a material property. Diameter tells us I can make how small I make this diameter, I will correspondingly reduce this value of beta. So this tells us what is the maximum diameter I can choose so that this beta is less than 1 to make it safe. Okay. Let's take some typical values and calculate. Okay. Here is the data, tube diameter if you plot versus heat of reaction, and this is the delta T max, if you like, what is allowed. Okay. So 220. This is 0 to 20, 20 to 40, 60 to 80. If I am allowed, let's say I have a reaction which is having a heat of reaction of minus 30 kilocalories per gram mole, somewhere here, and I am allowed to have a delta T max of, let's say, 60 degrees or 40 degrees centigrade, or let's say what is it, 40 to 60, 50 degrees centigrade, somewhere here. Maximum I can have a tube diameter is of 14 millimeters. But if my heat of reaction is 30 kilocalorie per gram mole, I am only allowed a delta T max of 20 degrees centigrade or 10 degrees centigrade. I can have maximum 4 millimeter tube. Same way the other way around. I can plot tube diameter versus rate of reaction and I can calculate what is my allowable delta T max if you like. What is my allowed maximum delta T? Correspondingly, I can afford to take a particular size of the tube. That's how these charts are to be used. Look at this, smaller and smaller tube sizes, I can afford to do higher and higher exothermic reactions, micro reactors, flow chemistry. That's what that buzzword is these days. Right? Smaller and smaller tubes, I can do higher and higher rates of reaction, and my allowable delta T, it is allowed. Let's say for a particular delta T that is allowed, I have to go to smaller and smaller reactor size. As the delta T reduces, allowable delta T max reduces, I have to go to smaller and smaller, because now heat removal is decided by this P. These are the additional considerations that come into picture. Same way for different parameters. Generate these graphs for yourself based on these formulae. Generate these graphs for yourself. So now, what is my reactor selection tree? We had seen this earlier. For slow reactions, we either go to batch because plug flow becomes unmanageable, several kilometers of length, or we go to well mixed reactors in series. If it's a fast reaction and temperature control is important, we go with plug flow reactors and then make them small micro reactors, so that surface area is enough, surface area to volume ratio is very high. If temperature control is not important, then we could use a well mixed reactor. This is allowed. Okay, so this is an additional consideration now that we have got from this lecture. Derive all the reactions, all the expressions for yourself. Make sure that you are able to plot graphs like these. Make sure you have understood each and every formula. What is the implication of each and every formula? Right? Think about all of these things. Take time to understand. This lecture time is maybe 1 hour. So just to give you some practice problems, use let's say Fogler's book, 4th edition, chapter 8, problem number P85, 86, 822A, and in 5th edition there are 2 chapters, 11 and 12. So do problems from this. Take time to understand. Take time to understand. So our lecture here is perhaps 1 hour, 1 hour 15 minutes or so. But if you derive all these formulae for yourself, try to understand the meaning of what we are deriving, trying to plot all the things that I have plotted, right? And make sense out of that in terms of what is there in a real life reactor. It will take you easily 4 or 5 hours to just study this lecture and make sure that you spend that much amount of time and understand what is being talked about, understand what is being discussed, understand the implication, derive. You should be able to write all these expressions for yourself. So these are the additional things that come into picture when we start talking about real life reactors. Real life. That's how it is. That's how this theory is a very interesting topic. It's not just well mixed and batch and plug flow and in first order, second order. So many additional considerations come into picture. Safety, stability of the products, right? Charring, smell, quality, all these things come into picture once we start talking about exothermic reactions, plug flow, well mixed, which one is better. Right? All these things now matter when we start. What is the surface area to unit volume, flow chemistry? These are the buzzwords that are used these days. It's nothing but plug flow reactors, but reactions are so fast that to do them, to make them happen isothermally or to manage the heat, I need to increase surface area per unit volume. I can only do that by reducing diameter of the reactor. So understand all these things. Understand all these things. Okay, so we'll stop here for this lecture.